Hello and welcome to MySaMaths Week 1 Video 2. This is Epsilon and today we'll be going through geometric sequences. So geometric sequences are introduced for the first time in matric. So we haven't seen them in earlier grades and this is your first exposure to them. So it should be useful for us to start off with a definition. What is a geometric sequence? So basically a geometric sequence is a sequence of terms in which each a spelling there, just write that here, consecutive term is obtained by multiplying, this is a bit of a long one, by multiplying the previous term by a constant ratio. Okay, so this is quite a lot of words. Let's break it down. So first of all, let me get out my highlighter. It's a sequence of terms, obviously, because we know what a sequence is at this point, and it's a geometric sequence, so we know that it's basically a sequence of terms. But it does have a bit of a different behavior from arithmetic and quadratic sequences, because in this case, to get the next consecutive term, instead of adding a difference, we multiply. And we're multiplying by a constant ratio. That constant ratio is referred to as R. So let's solidify this with an example. So the first example, let's say we have a sequence 1, 3, 9, 27, and so on. So what you'll see is that there's a common ratio between all of these terms. And for us to find that common ratio, what we can do is divide second term by the first term, the third term by the second term, the fourth term by the third, and so on. If we do this, we get 3 over 1, 9 over 3, 27 over 9, and all of these simplify to 3. So that means that our common ratio here is 3. So basically what that means is to get any term in the sequence, you just multiply the term before it by 3. So to get this 9, we'd multiply this by 3. To get this 27, you'd multiply this by 3. That's the common ratio. So basically that's the definition of a geometric sequence. So let's try and illustrate this. You'll notice that in this video we're using graph paper. So you'll see why that will come in handy. So let's say that we have a square. A square with area 1. We can think of the area as just the number of blocks that make up the square. Since this one has only one block, we can consider it to have an area of 1. So if we were to multiply the area of the square by 4, we would now get a bigger square with area 4. If we were to repeat this, my numbers are getting in the way. Let's shift this a bit downwards to make some space. Okay, so if we were to multiply this square again by 4, we'd get an even bigger square that looks like this. Oh, I'm overshooting it there. Okay, let's straighten this up a bit, make it look a bit neat. So that's our square. Not a very perfect square, but you get the idea. So if we continue this process, we would see that the size of our square keeps on increasing. So we would have, I'm not sure whether this is going to fit. Yeah, it isn't going. We've ran out of space. Let me try and move this a bit to the left. Okay, bit more just to try and align it. Okay, so let's see whether everything is matching up now. We need to extend that a little bit. Okay, I'm not much of an artist, as you can see. So the area of this square would be 32. So we see that in order to get the next area, just multiplying the previous one by 4, multiplying by 4, multiplying by 4. Okay, so what we see is that there's a common number that's multiplying the areas of these squares. And what you'll see is that these squares are not changing their shape. They're remaining as squares. They're just getting bigger. That's different from something like, let's say we had one square there, then instead of like multiplying the square, we add 2 more squares to it and add 2 more squares to that. Let me just section that off. Then add 2 more to this. You can arrange these blocks in whatever order you want. The point that I'm trying to bring across here is, in this case, where you're just adding squares, the shape isn't remaining the same. So let's look at it this way. What is the total area of this shape that we have here? It's 3, right? Just adding the number of squares if each square has an area of 1. So here we have 5 squares, so the total area of this object would be 5. Here we have 7 squares, so the total area here would be 7. What do you notice about this? We get 1, 3, 5, 7. And above, in our original example, we had 1, 4, 16, 32. Okay, so that just continues like that. And what you'll notice is the areas of the first figures here form a geometric sequence because there's a common ratio between all of the terms. All of the numbers are being scaled up by the same ratio. But in this case, we get something that looks like an arithmetic sequence. Here, the numbers are not being scaled up. They're just being increased by a certain difference, in this case, which was 2. As we could see there, our difference would be 2. Here, our common ratio would be 4 in our original example. So we see that fundamentally, if you think about this in the world of geometry or shapes, with a geometric sequence, you're basically taking an object and you're just increasing it in size, but it's keeping its shape, it's maintaining its shape. That's why here, all of these objects remain as squares. They're just becoming bigger squares. But here, we're getting something completely different each time. So that's one way of thinking about geometric sequences. It's a way of taking an object and multiplying it, scaling it up a bunch of times. So that's the diagrammatic interpretation of a geometric sequence. Okay, so enough about all of this abstract stuff. Let's get back to what we're used to, which is numbers and all of that. Proper numbers, not shapes. No shapes included this time. So, okay, now we've given some type of intuition, a visual intuition of what a geometric sequence is like. Okay, so we'll move on now to the properties of a geometric sequence. And we've covered a few of the properties already, which was the most fundamental one in the definition. And let me just highlight that, was that we multiply by a constant ratio. That's the most important property of a geometric sequence. So the one that I want to talk about now is slightly different. Okay, we know that there's a common ratio, right, between all of the terms. But that common ratio could take on many different values. Let's consider this sequence. Let me just use this one here. Let's say we have 2, 6, 18, and so on. And we're told that this is geometric. It's a geometric sequence. So obviously you would see that the common ratio here is 3, because we're multiplying each previous term by 3 to get the next term. So what you'll notice here is this sequence is increasing. The numbers are getting bigger and bigger. And you would expect that because you're multiplying each number. So you do expect it to become bigger. But there are some cases where this is a bit different. Consider the sequence 10, 5, let's say 2.5, 1.25, and so on. I don't really like the fact that there's decimals in this, but yeah, we can work with that. Okay, so what you'll notice here is that this sequence behaves a bit differently from this first one. Let's say that this one is geometric too. That's our assumption. And you can see that there's a common ratio, so it is geometric. But what you'll notice is this sequence, the second sequence that we've written here, is very different from the first. Because this one here is decreasing, while this one here was increasing. So why do we think that is? Why do we think the second one is decreasing? And the way we can sort of look into that is to find the common ratio of the second one and see how it differs from the common ratio of the first. Maybe that will give us an idea of why this one is decreasing. So here we get the common ratio to be 5/10, 2.5 over 5, 1.25 over 2.5, and so on. This gives us 1/2, 1/2, 1/2. Okay, so we see that these common ratios are quite different and they result in very different sequences. And as you create more and more of examples like this, you'll notice a pattern. Whenever r is between -1 and +1, the sequence will always decrease. The sequence will always decrease whenever r is between -1 and 1. Like in this example, our r was 1/2, and 1/2 lies within this interval here. So we would expect it to decrease because it satisfies this inequality here. And whenever r is outside of this interval, writing that mathematically, that would be r is greater than 1 or r is less than -1. We don't include the ones because if you just multiply in the sequence, if you're multiplying each term by 1, it'll just remain the same. And the sequence is no longer geometric or arithmetic, it's just a row of identical numbers. Okay, so that's why we don't include the ones. So whenever r is outside of this interval here, whenever it's greater than 1 or less than -1, the sequence will increase. And we have to be careful here. We have to be very careful, because when we say increase, remember that there are negative numbers involved. So we have to be a bit specific. We'll say that they increase in size, or we call it absolute value. Okay? So basically what that means is, let's say that let's just give some more examples to make this a bit more clear. So let's give examples where, let me change colors here just to make things a bit clear. Let's think of examples where r is between -1 and 1. Okay? So we can think of a sequence where r is equal to 1/3, for example, and we can have a first term of 9. Okay, so what does the sequence look like? Our first term would be 9. Second term would be 9 times 1/3, which is 3. Our third term would be 3 times 1/3, which is 1. Fourth term would be 1 times 1/3, which is 1/3. After that, we get 1/9, 1/27, and so on. So we can see that this sequence is obviously decreasing. So that means that this example confirms our original statement here, that the sequence will always decrease when r is between -1 and 1. But what you'll notice is it decreases, but it will never become less than 0. It will decrease, but it will never become negative, because all of these terms in the sequence are positive, and we're multiplying them by another positive number. So it's impossible for them to eventually at some point become negative. Okay? So even though they are decreasing, they will never go below 0. Okay? So let's look at another example. Let's use -1/3 in this case. We have a as 9. So we start off with 9. In this case, we have -3, then +1, then -1/3, then +1/9, -1/27, and so on. So in this case, we have a bit of a strange pattern, because we're fluctuating between negative and positive numbers. But what we see here is that, okay, we go from a larger number to a smaller number. Remember that as we go, every number that's negative is less than any positive number that you can ever think of. So we're going from a larger number here to a smaller one, -3. Then going back to a larger number, which is +1, then back to a smaller number, which is -1/3. So if you look at it that way, if you look at the signs, then you can say that this example goes against our statement here, because this sequence isn't decreasing, it's increasing and decreasing, then increasing again, decreasing, and so on. It's fluctuating. So what we have to do is look at these numbers in terms of their absolute values. Ignore the minus sign and just take the number with its magnitude as it is. So we would look at this as a 3, we'd look at this as a 1 over 3, and we'd look at this as a 1 over 27. So even though in actual fact these numbers are negative, the reason why we do this is so we can see that this pattern, if we were to ignore the negative signs, the pattern does hold, that the terms are decreasing, because we go from 9, 3, 1, 1 over 3, 1 over 9, 1 over 27, and so on. Okay? So let us see. So we have our two examples where r is between -1 and 1. So we do see that we do need to adjust the statement here, because it says that the sequence will always decrease. But it does become a bit confusing when the sequence begins to fluctuate between negative and positive. Is it still decreasing or is it not? So we can say that it's decreasing in absolute value. Absolute value means that we're ignoring the negative signs. Okay? So those are our two examples when r is between -1 and 1. So we can now look for examples where r is outside of this interval here. So that means that r is greater than 1 or r is less than -1. Okay, so there are plenty of examples of this. Let's say r is equal to 2 and a is equal to 3. So we would have a sequence that looks like this: 3 times 2, 6 times 2, 12 times 2, 24, 48, and so on. So we see that the sequence is increasing. Okay? And what did our original statement say? That if we have an r that's outside of this interval, the sequence will increase in size or absolute value, ignoring the negative signs. So we don't have any negative signs in this case, so we don't even need to worry about that. But we do see that the terms increase. Let's look at another example where we have r equal to -2, a equals 3. So we get -6 here, 12, -24, +48, and so on. So ignoring the negative signs, we see that these numbers are still increasing, ignoring the negative signs. Keep that in mind. Okay, so we see that our little property holds, but we do need to adjust a couple of things, because we do need to say that ignoring negative signs, the sequence will either decrease or increase. So let's go and write this down properly now. So if r is between -1 and 1, the absolute value, and what absolute value means is just we're ignoring the negative signs. That's all that absolute value is. So the absolute value of the sequence will decrease for each term. Okay? So I don't like the way this has been phrased. Let's make this a bit more clear because it does sound a bit confusing. So the absolute value of each consecutive term. Yeah, let's put it that way. The absolute value of each consecutive term decreases. Okay? Then if r is greater than 1 or r is less than -1, the absolute value of each consecutive term increases. Okay, so those are the properties of the common ratio. When the common ratio is between -1 and 1, the absolute value of each term decreases. All of the terms are getting smaller and smaller in size. That's if you ignore the negative signs, if there are any. Then, if r is greater than 1 or less than -1, the absolute value of each consecutive term increases. It becomes bigger and bigger, ignoring the negative signs. Keep that in mind. Okay? So those are the properties of r, and this might seem a bit abstract, confusing. You might be asking yourself, why are we even doing this? Why are we even learning about these properties? And you'll see that as we go on to learn about things like convergence and so on, this will come in handy. Okay? So just keep that at the back of your mind. So for now, let's move on to the most familiar part for number patterns, sequences that we all should be comfortable with, and that's finding the general term. This is our happy place. General term. We all smile when we see questions asking for the general term, or we should be smiling. So the general term of a geometric sequence, you'll be glad to find out that it's one of the simplest, if not the simplest, general terms of any sequence that you will cover in metric, or that you will cover in your syllabus for maths. So what does the general term look like? What is the shape of the general term? That's the general form, remember? And the general form for a geometric sequence looks like this: AR to the power n minus 1. Simple as that. Once you have R, and once you have A, that is, and you have R, you've found the general term. So let's go and look at some examples. Let's say we have, find the general term. Of the following geometric sequences, because we're going to do a few. Okay, so the first one, let's say we have 4, 8, 16, 32, so on. Very simple one. Okay, so Tn should be equal to A, which is 4, times R, and we see that just by some quick division, we can find our R to be 2. Don't confuse this with a common difference. This is a common ratio. Just label that as R equals 2, just to keep that in mind. So we have 4 times 2 to the power n minus 1. That's the general term. Simple as that. So let's look at another example. Let's say we have a decreasing sequence this time. Let's look at this sequence here: 1000, 100, 10, 1, 0.1, 0.01, and so on. So this is a geometric sequence, and it's decreasing. So if we were to find the common ratio, oh, skipped one there. If we were to find the common ratio between these terms, we would see that that is equal to 1 over 10. Okay? Just a little reminder, this 1 over 10 lies in this interval, which is why we see this sequence decreasing. Okay? Just a little recap of what we just did a couple of minutes ago. So the general term here, still as simple as the first one. First term is 1000. R is 1 over 10 to the power n minus 1. Simple as that. That's how you find the general term of a geometric sequence. As long as you have the first term and the common ratio, you can find the general term. So those are pretty much the basics on geometric sequences. So in our next video, we'll be moving on to series. We're moving out of sequences for a while and going into series, arithmetic series and geometric series. Okay, so till then, we hope that you'll be well and that we will be with you soon. Goodbye.